So we were yesterday figuring out how the band gap came. Right? And the basic idea was the following. We wanted to generate a p-tag voltage which is of the form VA minus VB, which is some VT ln n times K, and to this you have to add a VBE, right? So that the negative temperature coefficient of VBE is cancelled by the positive temperature coefficient of this VT ln something. And we yesterday by doing some math we found that you need to add about 23 VTs or 24 VTs to VBE so that the temperature coefficient of the resultant, which is VBE plus VP tag becomes 0, and that will give you about 1.25 volts as the constant voltage. That's the V band gap. And then we said, okay, our experience in the past has shown us that every time we want to get gain, voltage gain, what we have done is somehow converted a voltage into a current and passed that current through a larger resistor, and so therefore you get voltage gain. And so the first job was to convert the voltage VA into a current, and that we said we can do by using negative feedback. If this is VA, then what should be the signs of the op amp, which is plus and which is minus? VA is minus, VB is plus. Okay, so if this is, since this is negative feedback, what is the voltage there? And if the op amp gain is infinite, what is that voltage? VA. So this is a clean way of generating VA by R1. Correct? But what we want is the difference between, we want to convert VA minus VB into a current. Correct? And that's easily handled, as we saw yesterday, by doing this, right? So the current that will be flowing here is actually not VA by R1, but VA minus VB by R. Right? And we said that VB is straightforward to generate, is basically generating VB is straightforward. It is simply putting N diodes in parallel. Correct? So this is VB. And you have to subtract, and how do you generate VA? We need to pass the same current through a diode of size 1, correct? And to get the same current, what do? It's very straightforward. You mirror off of this transistor. If this size is X, this size is also X, and this, you put a diode of size 1, right? So this gives you, so what happens when everything is hunky-dory, this voltage and this voltage are the same, correct? And the current flowing in R1 is basically VA minus VB by R1, which is the same as the current flowing in the left branch. Therefore, the voltage drop across R1 is what? A minus VB, and what is that? This voltage drop across R1 is VT ln N. So that the current is VT ln N by R1. So this is a p-tag current. Okay, p-tag stands for proportional to absolute temperature, because VT is KT by Q, it is proportional to absolute temperature. Does this make sense? So in other words, we have taken this p-tag voltage, which is VT ln N, we want to multiply it by some number, right? So what do? We converted this voltage into a current, correct? And now converting it into a larger voltage into a multiple of Vt ln n is straightforward, because you take the same current and pass it through an appropriate resistor, so that the value of the current, the voltage is scaled up. Correct? And one way of doing that, as we saw yesterday, is to take, let me not be sloppy here, draw a clean diagram. Okay, so one way of generating the band gap, therefore, is to take this current and then pass it through a larger resistor R2. So all these three transistors are the same size X, and to generate, to this you have to add, so this voltage drop, if current is flowing through this, will be Vt ln n times, very good, Vt ln n times R2 by R1. To this you have to add Vb. Correct? I mean, so one thing, of course, you, I'm sure some of you recognize this already, is that what is this voltage? Vb. Is there some other node in the circuit where you have the same voltage? This voltage and this voltage are both also equal to Vb. Correct? So there is no real necessity to have a whole separate branch. What could I do? Very good, right? So you could, for example, generate tap of the band gap voltage like this. If you make this R2, which is the band gap? The top terminal of R2, that is correct. These two are the same size. This voltage is nothing but, this is VA, which is also VA by virtue of the op amp. So this voltage VBG will be R2 by R1 times Vt ln n plus Va, which is VBE. Correct? So this potential is VBE. This potential is VBE. By virtue of the op amp, this potential and this potential are the same. Correct? So that you have to add a Ptat voltage, which is a multiple of Vt ln n. And that multiple is nothing but Vt ln n by R1 times R2. Yes, sir. How do you know that there is DC negative feedback? Break the loop somewhere. I will break it here. And I will yank this guy up. What happens to this potential? If the gate goes up, the drain must go down. Okay. If this goes down, what happens to this voltage as it comes through the op amp? It goes down by a large amount. So clearly there is DC negative feedback. Correct? Okay. Now let's quickly compute the put some numbers in. So if this goes up by delta V, what happens to this voltage? GM? No, look carefully. What is the incremental impedance looking in? What is the quiescent operating point? What is I? Yeah. What is that? It's Vt ln n by R1. That's the quiescent current, right? So the incremental voltage change when the gate of the transistor, that node X there, is pulled up by, yanked up by delta V, is the incremental current will be Gm times delta V. That times the incremental resistance looking in at the drain. And what is the incremental resistance? What is the incremental resistance of this box in green? R1 plus? Okay, the incremental resistance of the diode is simply nothing but Vt by I, which is Vt ln n by R1. So that is simply R1 by ln n. Is that clear? The incremental resistance of diode is nothing but Vt by Ic, the quiescent current. Ic is nothing but Vt ln n by R1, right? Which means that the quiescent resistance, the incremental resistance of the diode, therefore, is Vt ln n, R1 by ln n. So what is the total incremental resistance? R1 plus. So this incremental voltage, therefore, will be Gm times delta V times R1 plus R1 by ln n. Actually, is it, I'm missing something? Yeah, that's fine. Does it make sense? Pardon? If delta V, if the gate goes up, the incrementally, the drain must go down. Correct? And the magnitude by which it goes down is GMP times delta V times R1 plus. R2 plus. Yes, she's complaining that you haven't considered RO of the transistor. For the time being, let's assume that the transistors are all ideal. Right? So that the R out is, the lambda is, is 0. There is no channel length modulation. So it behaves, the transistor behaves like a ideal incremental voltage controlled current source, and since R2 is in series with the current source, it doesn't influence the voltage at the positive terminal of the op amp. Is that clear? So now what is this voltage? Assume the DC gain of the op amp to be some A. It is minus, this voltage is also going down. The magnitude is GMP times A times delta V times R1 plus R1 plus R1 by ln n. Does that make sense? Yes, Amrut, you have a problem? You sure? Everybody is clear on this? There's nothing, there's no rocket science here, it's straightforward. Okay? Alright. So now let's get back to our situation, which is we have, okay, now let's add stuff one by one, right? I have broken the loop here, mind you. This is where I broke the loop. Now, and again I have applied delta V here. So what do you think happens at the output of the op amp now? Think carefully, people. No, think carefully. We are interested in finding the incremental change in the output of the op amp when I yank the gate, that node X, gate of those two PMOS transistors by delta V. So if I yank that voltage up, what do you think happens to this node? Goes down by this factor, correct? So what happens to this node? Look carefully, people. It's a voltage source. So what happens to that node potential? It's incrementally grounded, right? So if I did this, there is still no issue. This voltage does not change, right? This voltage changes by this amount. So there is, and what comes here is this quantity multiplied by A, as we had earlier. No, wait a minute. This is, at this point, this is a battery of value VA. No, I don't understand the confusion. This is not really a battery, it is a diode. Sorry. Okay. So what is the current flowing through this diode? Quiescent current? Vt ln N by R1. So what is the incremental resistance of this fellow? It is R1 by ln N. Incrementally this is R1 by ln N. Okay. So what happens to this voltage? The gate goes up. So what happens to that voltage? VA, I mean the negative terminal of the op amp goes down by GMP times R1 by ln N. Okay? Alright. So what is happening now? So now can you comment on what happens to this voltage? Yeah, sure. Into delta, correct. Alright, now can you comment on what happens to the, so if this node potential is decreasing, what will happen here? It will tend to increase, right? This, if I yank the negative potential down, the output of the op amp will tend to increase. However, the op amp is not responding to either the absolute potential on plus or the absolute potential on the minus. It is responding only to the difference between the two. Correct? Which means, therefore, what happens to the output now? The left node is going down by GMP times R1 times delta V by ln N. The node on the right is going down by GMP times delta V times R1 plus R1 by ln N. So the net difference in the op amp inputs is, GMP delta V times R1. Correct? So what happens to the output voltage? It's A times GMP times delta V times R1, and that's what happens here. Right? So now is this negative feedback or is it positive feedback? It is negative feedback. Okay. So please note that as one of my friends pointed out yesterday, there is positive feedback through this path, because if I yank delta V up, okay, if for example I had held this node fixed constant, right, if this node was held constant, then there's definitely positive feedback, because if I yank this guy up, this guy goes down. If this guy goes down, and these are the signs of the op amp, the output of op amp goes up. So through this path on the left, there is definitely positive feedback. Through the path on the right, there is negative feedback. Okay? Alright? And in this case, you could argue that the gain of the positive feedback path is smaller than the gain of the negative feedback path. Okay? That's one way in which you could argue.
So in general, is that true that whichever loop gain is small will eventually?
Yeah, well, I mean, see, there are several ways of arguing about this. I mean, one argument that I could present, right, is to say the following. There is definitely negative feedback here. All right. The next thing is one of those strange things. Okay. See, this, by virtue of the op amp, this voltage VA, let me call this M and N. So by virtue of the op amp, Vm equal to Vn. Correct? So in other words, if you were given the circuit without deriving it from first principles, right, how would you go and proceed to find the quiescent operating point? If I gave you a new op-amp circuit, what will you do? Come on, people. And what? If I give you a circuit with op-amps, what is the first thing you will do to find output versus, input-output characteristics or whatever? Assume virtual ground, okay, and assume that there's negative feedback around the op-amp, so the two input voltages are virtual shorts, right? And write the equations and then figure out what the operating point is, which is what I will do now here. So Vm equal to Vn, correct? And by virtue of the two transistors having the same gate source voltages, okay? Assuming again that the transistors are in saturation, the two currents will be the same, which means that Vm equal to Vn, and what is Vm? It is Vt ln whatever current I is flowing divided by Is, and this must be equal to IR1 plus Vt ln I by NIS. Correct? This is the equation I would write. So what are the solutions to this equation? Clearly one solution is, the solution is I equal to Vt ln N by R1. Okay. But there is also another solution, and the reason why we are not seeing that here is that the true equation is basically Vt ln I plus Is by Is, and similarly this is I plus NIS by NIS. This is the correct equation. Why? Because the I versus V of the diode is nothing but Is exponential VBE by Vt minus 1. Okay? Alright. Normally, if a lot of current is flowing through the diode, then that I plus Is can be approximated by I. Okay? But this happens to be, but here is a situation where you are trying to find I. Okay? If you knew I was very large, then you could use the approximation, but here you are trying to find I, so you don't know whether I is large or small. So now can you solve the equation?
A equal to 0.
I equals 0 is very much a solution to this equation. Another way of seeing it, you can verify clearly that when you put I equal to 0, you get 0 on the left side and 0 on the right side. Okay? And a way of seeing that in the circuit is that if I is 0, this potential is 0, correct? Which means this potential is also 0 because this voltage is 0, this voltage is 0. So the left potential and the right potential M and N are at 0. So the op-amp input terminals are at 0. So the op-amp is happy, correct? And basically, everybody is happy. Okay? And for example, this being 0 and this being 0 and this being VDD, for example, is a valid solution to all the Kirchhoff's equations. You understand? So apart from the desired solution, which is this, why is this the desired solution? I am presuming that you want the band gap voltage and not ground, right? If I was 0, then what will the output voltage be? Krishna Karthik, what will the output voltage here be? 0, right? Because the drop across R2 is 0 and so is the drop across R1, right? So the argument would be, if I want 0 volts as the output, I didn't have to go through all this trouble, I will just connect the wire to ground. Okay? So the assumption is that you actually need the band gap voltage and not 0. Therefore, this solution of I equal to 0, which seems like a possibility, okay, is definitely something that you do not desire. You need the circuit to settle into the other solution, which is Vt ln n by R1.
So, but when both inputs are 0, the output should be 0.
No. This this is an infinite gain thing, right? So the output can be anything, and the input voltage will still be 0, isn't it?
Yeah, but both are exactly the same.
Same. Yes, the output can still, for example, in the op amps that we have discussed, right? The two inputs are the same. The output can be anything between VDD minus delta V and VCM minus delta minus VT. Okay. So this is a valid concern, right? And so there is definitely a possibility that this circuit gets stuck. There are two operating points in the circuit. The summary, therefore, is that there are the circuit has two operating points. Yes. No. So the question is, what do you call the two valid operating points? Is it only true when there are diodes? It turns out that whenever you have a nonlinear element, okay, you have the potential for having multiple operating points. Okay. In some cases, several of these operating points can be stable, whereas in other cases, depending on circuit topology, most of these operating points will not be what are called stable operating points. I'll basically discuss what I mean by stable and unstable operating points with a quick analogy. But in this circuit, right, we've calculated two operating points. One is the all zero operating point, which is useless, which is not the desired operating point. Okay? And the other operating point is this current I being equal to Vt ln Vt ln n by R1. Okay? And you want to make sure that the circuit actually eventually reaches the desired operating point where there is a finite current flowing through I1. So one way of so what do you suggest we do? One way is to argue that, hey, let's take a look at the circuit a little bit. Let's say the circuit is actually stuck in the operating point which is not desired. That is, this voltage is 0, this voltage is 0, and this current is 0. Correct? What do you think will happen if I inject a small current here? This potential will go up. Right? What will happen to this potential then? It will come down. If that potential comes down, what do you think will happen? Current will flow in both these transistors, and what will happen? It will get kick-started to and go back to the desired operating point, which is Vt ln n by R1. And once it is in the desired operating point, okay, there is indeed negative feedback around the op amp. So small perturbations around that operating point will cause. When there is negative feedback, what does it mean? It means that for small perturbations, there is a restoring force pulling the circuit back into the original operating point. That's what it means. Correct? So if there is a small current which flows into one of these nodes, right, then automatically the circuit will jump into its stable operating point. Okay? So therefore, as I've shown intuitively here, one of the operating points is unstable. Okay? So an unstable operating point, the analogy is this. Let's say you have a hill, right, or a steep surface, I mean a curved surface like this, and you have a ball sitting here, right? The ball sitting on top of the hill is definitely an operating point, right? You can actually make the, what do you call, the ball actually sit on the top, right? But even a small wind blows, what will happen? Ball roll off from the top, right? Whereas this is a stable operating point, actually not that, but stuff is actually touching the valley, right? So here also the ball is sitting at the extreme, I mean in the valley, but small perturbations will cause the ball to come back to the original operating point, right? So this is an example of an unstable operating point, and this is a analogy to illustrate what is meant by a stable operating point. If you have an unstable operating point, even a puff of air is enough to push the system out of its unstable operating point. Okay, and if you have a stable operating point, it will be the operating point will not be disturbed for small perturbations in environmental conditions, so to speak. Does it make sense? So in our circuit, what do you think? We've already seen that the all zero operating point, which is not desired, is fortunately an unstable operating point. So even a small perturbation will cause the circuit to settle to its stable operating point. Okay? Why? Because if I inject a small current into this node, this potential will rise, causing this potential to fall, causing current to flow into both these transistors, into both these diodes, pushing both the potentials up, right? And then the op-amp basically figures out that this potential and this potential are not the same anymore, right? And it goes and varies this gate voltage until the two potentials become the same.
So would it be unstable even with respect to a small perturbation on the other side?
Yes, it will be. Okay? So you can go and think about it. It's actually quite straightforward to show that when I is 0, the operating point is unstable. So is this a good thing or a bad thing? That the undesired operating point is unstable. It's a good thing, right? Because the circuit naturally doesn't want to sit in that situation. Correct? So what do you think we should do about it? I mean, should we do anything about it, or can we just let it go?
Even there might be a very small and usually negligible current to the.
See, one argument you can make is that a small current pushing into any of these nodes is enough to kickstart the whole thing, right? So, and anyway you know that with all devices there will be leakage currents in PN junctions which will push minute currents into all nodes, correct? So in principle you would say, hey, I just let it go like this and I should be okay. But unfortunately it turns out that by Murphy's law, if you want the stable operating point, the circuit will almost always get stuck in the unstable operating point, and if you want the unstable operating point, the circuit will go into the stable operating point, and these are chances that you do not want to take. Correct? I mean, you see, finally the band gap here is, from this you're generating a whole bunch of bias points in bias currents and bias voltages that your circuit, your big analog system needs on chip. So if the band gap doesn't start up, then the whole chip doesn't start up at all. Okay? It might be a very simple circuit on its own right, but a lot depends on the band gap. So you do not want to take chances at all, and especially when these things are supposed to be operating at very low currents, at very low temperatures. Leakage currents, as you know, rise exponentially with temperature, which means that at very, very low temperatures, the leakage current may be so small, right, that either the band gap may not start up at all, right, and quite perversely it sits in that unstable operating point for some strange reason, just to frustrate you, right, and doesn't get out of it at all. And the band gap is 0, bias currents are 0, your whole system is dead. Okay. So you need, so while it is true that the operating point is unstable, you do not want to take any chances at all, right? So you need to have some special circuitry to make sure that the current is indeed not 0. That's very straightforward to do, right? So one way of doing it, I mean, if this fellow is sleeping, what do you do to wake him up? One way is just shake it, right? Okay, when I say shake it, you electrically shake it, not physically. So one way would be to simply yank the supply up and down, right? So some current will flow into some of those nodes, and because it's unstable, it will. Okay, it's like saying I have a ball which is sitting on top of a hillock. What should I do to make the ball roll down? There are a million ways of doing it, correct? Okay. So it's quite straightforward to figure out a circuit which will measure the current that is flowing here, correct? Okay, and inject current into one of these nodes or both of them, so that the potentials rise up, and then the circuit will do its thing and settle into the stable operating point. And once it settles into the stable operating point, what is it supposed to do? What am I supposed to do? I'm supposed to just leave the thing alone and let the circuit do its thing. It's like this: if you have a scooter, right? Of course now you have electric start, but you have to. There are two operating points in a scooter, right? I know that's what you like to think. One is when the scooter is started and is ready for operation, right? Or it is all dead, right? There are two operating points. Okay, and in this case both of them are actually stable operating points. Okay, so to get from one point to another, you need a startup, a kickstart, right? Or like you people, or like me, for example, for that matter, in the morning, like when I get up, I just can't do anything. You know, if there was no coffee, I would just basically, probably sit and read the newspaper until it's 2 in the afternoon, right? But to get into the groove, a cup of strong coffee is what makes a lot of us tick, I would think. So like that, you need, the circuit also would be sleeping. So you need somebody to give it that shock once in a while to get it back into operation. Or like quiz 1 in our academic lives, right? So people are sleeping until quiz 1 and then they're like, whoa, what happened, right? Okay, and then you pull up your books and start studying. Okay, so this circuit basically has two operating points, and there's nothing, it turns out that there's nothing special about this two. In fact, I think there's a lot of theoretical results. People have figured out if there are n transistors, how many operating points are possible, and that's a whole new area in itself. But it turns out that if you have many transistors, you can have many operating points. But thankfully, the desired operating point is only one. And in this case, it's either the all zero operating point or the desired operating point. So, I mean, the one way of thinking about this is that, for example, if you are working for a manager and the manager is always not happy with what you do, okay? So you do this way and he says, oh man, you're a sloppy guy, you don't know what you're doing, why don't you do a better job, right? So there are two ways around the problem. What are the two ways? I can think of two solutions to this problem. I mean, non-violent solutions to this problem. Yeah, so one thing is to say, I will really slog and, make sure that my manager is very happy. Okay? And that is the good way of doing it. Another, which is a stable operating point, right? The unstable operating point is not do anything, because if you don't do anything, your manager can't find fault with what you don't do. You understand? Right? So that is the other way of solving the problem, right? Which is basically what is happening here. One thing is that you want to keep the op-amp happy, right? In which case, op-amp is only happy when its two terminals are the same potential. One way of keeping it happy is to have no current at all, correct? And the op-amp is happy because it sees both the voltages are the same, I don't want to do anything, right? The other solution is when both the voltages are equal to VBE, in which case the current flowing is not the zero current but VT ln N by R. Okay, so we'll look at what simple circuits you can use to kickstart this fellow and push him out of the slumber state. Okay, in the next class, which is tomorrow. Okay, thank you.